on your signal. Welcome to this session of Chai and Why. I know you must have braved usual mega blocks, but today is another unusual day, and our partner in crime, Arnav, is running the marathon. So he's, I don't know, I think still some time back we know that he was still on the track. Anyway, so the next few sessions, most importantly, tomorrow is a DP Roy Memorial Talk given by a Hungarian physicist. His name is pretty difficult to. His Saki. He is spelled C-S-A-K-I. Saba Saki. He is talking on particle physics at Crossroad at 4 o'clock in the Homi Bhabha Auditorium of Tata Institute of Fundamental Research. A fortnight later, it's the 5th Sunday, and as usual, this Sunday we'll have something from our lab. And coincidentally, we are showcasing Vijay's lab, quantum lab in the TIFR. So it's a, though he's not going to talk, he's different, but his lab is there. Following that, the transistor has completed 75 years, and we have none less than but a decorated person, V. Satyanarayana, who also happens to be a very high-profile member of the IEEE organization, and he's going to give that talk at the Prithvi Theatre, all at 11 o'clock. Today's speaker, Vijay, is alumni of the various different places. He graduated from St. Stephen's College in Delhi. After that, he has been to 3 different places, and he visits those time and again: Cambridge, Yale, and UC Berkeley. He is not just a physicist. He has many different hats to wear. He is a music composer. He is a beautiful musician, very accomplished. He also started, pioneered the conduction band because he's from the same field. So he and Arnav again partnered to begin the conduction band. So today he's going to throw some photons and light up something. Okay. So all yours, Vijay.
Thank you, Suren. And thank you everyone for being here and braving the traffic restrictions on this marathon day. They were asking me why I didn't run the marathon. I said, oh, this talk was too important, but I did run it once many years back and decided that was enough experience for me. So welcome. And this news is already quite old. You've probably already heard many talks, read many articles. And this topic, as I'm sure many of you know, quantum mechanics is controversial, is weird, strange, fascinating. Lots of things are happening these days, especially, which is also there in the public eye, especially with the development of quantum computing and quantum communication technologies. So I'm going to try and give you the essence of why this Nobel Prize was awarded, what was important in the accomplishments by these 3 scientists here. And we will try not to delve too much into the philosophical aspects of quantum mechanics, though I will mention, because some of the objections to quantum mechanics actually led to the series of experiments which were carried out by these 3 scientists, and based on proposals by other scientists before them. So it's important to briefly touch upon that. So I will try to start by giving a very quick introduction to what quantum mechanics is in the essence, which is relevant for this talk. And then we will talk about historically what happened and why these experiments were important and what they actually showed about the nature of reality or the nature of the universe we live in. Okay. So I also wanted to acknowledge Professor Sushil Majumdar, with whom I gave a talk for our TIFR audience a couple of months back. And the experiments here are actually all in the optics domain. They use laser light, and that's actually not my core area of expertise. So I learned a lot by discussing with him when we were preparing for that presentation. So I want to thank him, and hopefully I can pass on some of that knowledge here. Okay. So before we delve into the details, I want to give this entire story in just 2 slides, just 8 points, which highlight the essence of what happened and what was done. Okay, so quantum theory, which was developed primarily to explain how things behave at the subatomic level, and this was because people found that they don't seem to follow the usual laws of physics which were known in the early 20th century. And one of the predictions, and we will talk about this in more detail later, was this thing called quantum entanglement. And very simply put, it predicted that there was very strong correlation between properties of 2 particles if they are entangled. And that was a fundamental prediction which came out of the mathematics of quantum mechanics. When one looked into that in a little bit more detail, it turned out that when you talk about measuring the properties of these entangled particles, so typically we consider 2 systems to be entangled, but there can be more as well. Then we start talking about measuring the properties of one of them, it appears as if something strange is happening, which is faster than light communication. In the sense that this strong correlation, the only way people could sort of really understand it at that time, it looked like somehow measuring something about one of the parties of the entangled pair did something instantaneously to the other. Okay, this was really the primary objection, and the person leading this objection was, famous Einstein, because he had by that time developed the special theory of relativity, which clearly said that nothing could travel faster than speed of light. So then, how is it that in this entanglement, understanding of this entangled particle, especially the properties when you measure on one side, how is it that it is affecting something, or at least it seems to affect something instantaneously? A very important thing to keep in mind is that at that time, this is now the 1930s, no experiment on any entangled system had ever been done. It was not possible. The technology did not exist. Nobody even knew how to go about doing these experiments. These were all basically thought experiments and making projections based on what you understand about quantum mechanics, right? So Einstein, Podolsky, and Rosen in 1935, I think, they wrote a paper, and they said that because entanglement interpretation in this form, which suggests instantaneous action on another object, irrespective of how far they are, seems to suggest that there is something wrong with quantum mechanics, or at least it's incomplete. That the way we have the quantum mechanical picture as of now is not the full story. There is something else going on. And they suggested this idea of hidden variables. And this idea basically says that there are some additional properties of these systems which we don't seem to know. We have not figured out what they are, but they must exist. And it is those which are deciding this correlation. Okay? So this was proposed by them, and they said that quantum mechanics must be incomplete. And pretty much nothing happened for 30 years. The reason this was not a huge problem, that on the ground, it made absolutely no difference. This was really about the interpretation of what we think is actually happening. If you could carry out any experiments, and as I mentioned, there were not that many, it was not possible to do experiments to really test these ideas very clearly. But other quantum mechanical experiments were carrying out, and none of this interpretation had any real effect on the results of the experiment. So, people were not very worried or bothered about it. It sort of went in the background. And then 30 years later, John Bell, yes.
This hidden variable was suggested by this trio, or it was suggested by other?
There were many people who also suggested it, but that was, I think, the first time they suggested that something like this, I think this phrase was coined.
Something is wrong, something is not there.
Yeah, they said it's incomplete, and the incompleteness, the name they gave it to it, that there is some hidden variable. It will become a little bit more clear what exactly I mean by that as we go along. John Bell in the 60s, finally, he was reading this paper, and he figured out that actually it is possible to conduct an experiment. He gave a prescription where he could clearly distinguish between the prediction of quantum mechanics as we understood it then, and prediction of any hidden variable theory which may come up. Remember, none existed in a concrete form. So we will see what it exactly means, like what exactly we need to put in. And he said that it is actually possible because till that time, really, there was no way to even test the differences, right? So he finally gave a prediction where he said that if you do this experiment, then if you get this result, then it is clearly saying that hidden variables is correct. And if you get this result, then it means that quantum mechanics is correct and hidden variables cannot explain what we see in experiments. So this was a major and a very strong statement which he made. Again, there was really no way to test the experiments at that time. But after that, some experiments started happening. And then finally, the first experiment was done by one of the Nobel laureates, John Clauser. He did the first experiment, which confirmed that hidden variables cannot explain the results, or the interpretation of quantum mechanics, the way it was at that time, is indeed correct. Okay, so this was in the 70s. And then I think another 10 years later, Alain Aspect, the second Nobel laureate, improved these experiments. He introduced some new experimental techniques, and there was some important loophole, and I'll explain that a little bit later, which basically still left room for some alternate explanation. So the problem here is that you had to rule out all crazy possibilities to say that, okay, the only the quantum crazy part is correct. Okay. And then finally, Anton Zeilinger also further, I think in the 90s, did lots of experiments, made dramatic improvements to the quality of the experiment. And one of the things I'll emphasize as we go along is that the how these experiments actually give you an insight into how science works. As you make incremental progress, as you improve things, you understand things better, and that allows you to rule out certain things better and better. You could still have some doubt, and this is sort of one of the essential features, that there's always some room. Okay, sometimes people, they take that room to extremes and then propose something quite crazy. But these series of experiments really tells you how, is a good example of how science progresses. And in this case, over a very long period of time with small technical improvements. And then finally, Anton Zeilinger also used this idea of entanglement to do something interesting, particularly this idea of quantum teleportation. Okay. So all of these experiments confirmed that this hidden variable theory, or if any such hidden variable theory, cannot explain the results of the experiment. Only the quantum mechanical way of calculating things explains the results, and quantum mechanics sort of prevailed. So the Nobel Prize essentially recognized the experimental effort which went into proving the proposal which was set forth by John Bell. In fact, it's unfortunate that John Bell died in the 90s. Otherwise, he would have clearly also won a Nobel Prize for actually making that prediction, because that was a very key realization to say that you can actually test the difference between the two. Earlier, it was not even clear how would you go about distinguish between these two ideas. Okay, so that's sort of the story in brief. We will now go into things in more detail. So we have to start all the way back and talk about quantum mechanics and quantum physics, what it was all about, right? So we often learn this in high school, this what we call often the solar system model of an atom. You have a nucleus in the center with your protons and neutrons. So it's a positively charged center. And we typically think of electrons as going around in circular orbits around the nucleus, right? And the attractive forces between the positive and the negative charge and the motion of the electrons sort of keep things in balance, just like planets stay in an orbit around the sun, where the attractive forces of gravitation are pulling them, but the rotational motion keeps them apart, and you sort of balance that. So it seems logically, it seemed to be correct, but people realized that there were flaws in this argument, especially that if a charged particle is going around in a circular motion, it's accelerating, and it's supposed to emit radiation. And if it emits radiation, it's supposed to lose energy, and ultimately all the electrons would fall into the nucleus. And we, of course, know that that doesn't happen. So it was clear that this picture was not correct, that we cannot really think about electrons as going around in this very well-defined orbit around the thing. Bohr actually made some modification, and he said that only certain orbits are allowed, but he didn't really give a mechanism for why that is happening. That came later with the true quantum description, which was produced by Erwin Schrödinger. And that changed the model from the electrons going around in these well-defined circular orbits to talking about electron probability clouds. Okay, the picture here is basically showing where the electron can be found. It does not say anything about where the electron is. In fact, the quantum description said that you cannot ask that question, or that question has no meaning unless you carry out a measurement to find out where the electron is. So these 3D sort of plots tell you the distribution in three-dimensional space around the nucleus of where the electrons can be found for different orbitals, right? So these orbitals are labeled here. These are all very excited states of some nucleus. And it says that, there is this torus kind of thing, and there is this little ball here, like a teardrop here, and the electrons can be found in this region with varying probability, but it cannot be found here, or it cannot be found here. So it only gives you this probability distribution of finding the electron. And this was described by the famous Schrodinger equation, which was a wave equation. And this quantity, which is plotted here, is actually the square of this wave function, which is a solution to this equation. Okay. Now, throughout this talk, there are going to be many equations. Most of them are there as placeholders. So don't worry about it too much. Don't get scared. Most of them are placeholders or are very, very simple. I'll try to explain what it means. We'll, of course, not go into the detail of the Schrodinger equation. It's just there because it's a famous equation. The important thing to remember is that this equation gives you these probability distributions, and that's it. Within this cloud, we cannot say where the electron is at any particular time. We cannot track its motion. If we make measurements, and we have to do it many, many times so that we can construct a probability distribution, and then you can see that this probability distribution from the experiment will agree with what is predicted by the wave function from the Schrodinger equation. Okay. So the moment this was accepted, or we say that this is the description of the atomic world, because it's a wave equation, it's a linear equation, the mathematical properties of this equation tells you that if there are two solutions which are possible, then any linear combination is also a valid mathematical solution. Okay, this is purely from the mathematics. But then if you take that into the reality of what does it mean, that's where the whole strangeness of quantum mechanics starts to come in. So we are now going from the fact that the electron itself, say in this orbital, could be anywhere in this cloud, to saying that now it is possible. So basically what I'm saying is that this is one solution of the wave equation. This is a different solution of the wave equation. But it is now possible to create a situation where the electron is actually in a combination of these two wave functions, which means it could be in this orbital with this distribution, or it could be in this orbital with this distribution. And that is a possibility. And such states are called superposition states, right? So it's taking the strangeness to the next level, where these orbitals could have different energies as well. So we are now talking about the electron being in a superposition of two different states with different energies. They could be at different distances from the nucleus because of the shape of the orbital. In one orbital, you could be closer to the nucleus. In another orbital, you would be further away from the nucleus. So these things are now possible because the wave function allows it. And there is only we get very confused or bothered by this, because in plain English or whatever language we speak, the only way we can say is that it looks like the electron is in both places at the same time. Right?
We are talking about the superposition of the wave.
Exactly. Okay. So the superposition is the first step before we get to entanglement. So wave functions from Schrodinger wave equation describe quantum mechanics that allows for superposition, and then that's where we will go on next. So what is this quantum superposition, and how we can sort of write it down and think about it? Okay. Now, as Suren mentioned, I work in the field of quantum computing. And in quantum computing, we often use a quantum two-level system, but that is a good model for understanding all of this physics as well. Okay. So this is now just a cartoon. It's saying that, okay, I have some atoms. It could be any system. Right now, we can consider them. And there are some energy states in which these electrons can be. These are all solutions to the wave equation. And we take the lowest two energy state and we label them as 0 and 1. So this special symbol here, this bracket notation, signifies that these are quantum wave functions. So there's a quantum state, which means that I can have the electron in the lowest state, I can have it in the first excited state, but I can also have it in a combination of this 0 and 1, which can be written as a linear combination like this, where alpha and beta could be two complex numbers. And this is how we write a superposition state. And the way to visualize this two-level quantum system is to use what is called a Bloch sphere. Okay, just think of this as a globe. And these two states which we started off with, which are the two states of the electron in the lower energy and the higher energy, they are labeled as the poles of this globe. So south pole here is 0, north pole here is 1. And then all other points on the surface of the sphere can be thought of as different superpositions with different values of alpha and beta. Because remember, I said that you can take a linear combination. It could be any linear combination. So alpha and beta can have any values, provided their sum squares adds up to 1, because the total probability has to be 1. Because it basically means that the electron is either in the 0 state or in the 1 state. If you add both the probabilities, it should add up to 1. So if you keep that in mind and this picture in mind, it is possible to rewrite this in this particular form, where the position or the particular wave function describing this two-level system can be parameterized in terms of these two angles, theta and phi. So theta is like the angle in this direction, and phi is like the azimuthal angle. It is exactly the same as uniquely defining a point on the surface of the Earth using a latitude and a longitude. Right? Every point has a unique latitude and longitude. So similarly, you can think of this, that every point here has a unique theta and phi, and that determines one particular type of superposition state. So there are infinitely many possible superpositions. Okay, but that's what it usually means. Yes. So the question, whether I'm going to repeat the question so that the audience online can see. The question is, are alpha and beta the probabilities? They are actually called wave function amplitudes. The probabilities are the modulus squared of them. So the probability of being in 0 is mod alpha squared, and probability of being in 1 is mod beta squared, if alpha and beta are chosen in such a way that mod alpha square plus mod beta square is equal to 1. Okay, so you have to square the amplitude coefficient in this.
And that is why we are taking the sphere.
Exactly. Exactly. In fact, if you look at this equation, this will always satisfy, because modulus of cos theta square 2 plus modulus of sin theta square 2. This is a e to the I phi has a modulus of 1. So cos square theta plus sin square theta is always 1. So this equation basically maps onto this surface of what we call as a unit sphere. Okay. So that's just a visualization. Yes. Alpha and beta can individually be any complex number, but a modulus of a complex number is a real number. Okay. And then it's squared as well. Okay. So for example, this state here, which is exactly in the middle, would be what we often call as an equal superposition state. This kind of state would have a modulus of alpha square equal to modulus of beta square, which means the probability of being in 0 and 1 is the same. It's equal, and it's 50% each. Okay, but you can have this state anywhere on the surface of the sphere, and that would be a valid superposition. Okay. So now we go on to learn about another concept. Yes.
That is the problem. Then the circumference will be larger. So the probability that they are equally in 0 and 1 that higher than what is near point. So there will be far more points on the circumference of the node itself, and say we take something at a higher level.
Okay, let me see how to explain this. So the point you choose is actually up to you. You can prepare the system in any of these points. Now, there are actually infinitely many points on the sphere. So to say that there are more points on the equator as opposed to the other points is not really a strictly correct statement. But that really doesn't matter, because in experiments, you can prepare the system in precisely any of these points you want. There are ways to do that by controlling some quantities. Yes. So you're asking that does the electron wave function suggest in this case that it should be in all the states at the same time? So I have chosen a very particular system here, which has only two energy states. Okay. Now, I think I know what you're getting at. This is actually a slightly confusing point. And I'll go back to the previous slide to maybe comment on this. I'm talking about this being one energy state and this being another energy state. Within that state, I'm not saying anything about where the electron distribution is at all. Okay. So in this sense, we are actually not talking about the spatial distribution of the electrons. We are talking about which is the energy state it is in. So we are only concerned about whether the electron is in this lower energy orbital or in this higher energy orbital. And that's what these two states here are representing. Now, when we move to the block sphere picture, each point here is a unique superposition. Okay, so we are not doing superposition of superposition states. It's not that I'm creating a superposition of this point and that point. A single point here automatically determines an alpha and a beta, and it's giving you the relative weights of 0 and 1. Now, all the points on the equator are equidistant from alpha and from 0 and 1, like the two poles. And that basically tells you that the cos theta term and the sin theta term will have the same value. The square of that will have the same value. So that means that this superposition states which are all on the equator. So this angle does not matter for the probability. But if you have a state which was closer to the one pole, then it would have a higher probability of being in the one state and the lower probability of being in the zero state, and vice versa. Okay, so that's what it is. We are not talking about superpositions of different points here. Okay, this space of the globe is not the spatial wave function of the electrons, which just the energy. Now, these kind of states are often labeled in many different forms. They are called 0 and 1. Sometimes they are called H and V when we talk about these states in photons, in light. So H and V stands for vertical and horizontal polarization, or they could just be called spin pointing along X and spin pointing along Y. So there are many such nomenclatures. I thought I'll just mention that here because you might see these in different talks in different places. So an important thing to understand now is when we take a superposition state, what does it mean in terms of the probability we have assigned to it and what happens in an actual measurement? Okay. So if we start with a system in the ground state, okay, and this is a well-defined state now, it's not a superposition state. I should not use the term well-defined because even a superposition state is well-defined. It's just that this is the one of the standard, if you want to say the non-classical type of states here. So you prepare the system in the zero state and then you make a measurement. Okay, again, measurements are of many types and we will see that in a little while. But here we are, because remember I told you the two electron states are differing in energy. So you can think of this as a measurement of the energy. And it has only two possible values. It can have the energy corresponding to 0, which we can just call 0, or it can have the energy corresponding to 1. So if you start in 0 and if you measure it, what do you expect to get? It should be 0, right? It is in 0 state. So if I make a measurement, I should get the answer 0. Okay. And if I measure it again, if I repeat the measurement, I should again get the answer 0. So this is a well-defined state. These are often called the eigenstates of the system. Okay, these are not superposition states. Same way, if I now prepare the system in the excited state and I do a measurement, I will get the answer 1. And I'll get the answer 1 every time. Okay. So this is the simple case which we also understand in classical physics, that if something has a certain value, you measure it, you get that value. Now, when we go to a superposition state, and now I have written down this equal superposition state as 1 over root 2 0 plus 1 over root 2 1, because sum square of 1 over root 2 will give you 1. Now, if I make a measurement, there is now a 50% chance that the result will be 0. But if I now repeat the measurement after the first measurement, I will still get 0. Okay. This is what we call as the collapse of the wave function, because after this first measurement, the system has changed from this to this. So the result of the measurement also forces the system to go to the state corresponding to the measurement result. But I could have equivalently gotten a different answer. So if I now go back to the beginning, I again create a superposition state. And this time I could have gotten 1. And there is basically a 50% chance in the first measurement of getting 0 or 1. But after getting 1, if I repeat the measurement, I will again get 1. Because now the system has collapsed to this state. And it's now this fixed eigenstate, and it will stay there. So the results of sequence of measurement is very different. If you start in 0, you'll always get 0. If you start in 1, you'll always get 1. If you start in a superposition state, the first measurement will give you randomly 0 and 1. But after that, it will give you the same result as before. This is all, of course, in the most ideal case, and that's what we are talking about.
Random or 50%
Chance is random, right? When we toss a coin, there's a 50% chance of head or tails. In a particular toss, we don't know whether it's going to be head or tail. So you have to toss it many, many times to realize that it's going to be 50%.
But this is first time. After that,
after that, it will continue. But how does one verify this 50% measurement? You go back here, measure, and you say how many times you got 0 and how many times you got 1. And you will see that if you created an exact 50-50 superposition state, the experimental result will tell you that it is 50-50 superposition. Okay.
So every time you have to do the measurement, you have to reset it back to where you are.
Exactly. If you want to construct this probability distribution, you have to reset the experiment. In fact, this experiment right now only tells you that this point is midway between 0 and 1. It doesn't tell you anything about where it's pointing. Okay, so there's actually a more detailed set of experiments which involve measuring other quantities, and you have to repeat this. And this process is called quantum tomography. So this is something very important to remember, that a quantum wave function cannot be determined with a single measurement. You need many, many copies of it. You have to be able to repeat it with exactly the same initial state to actually know what that state is. So this is the important point. Okay.
You are able to bring it to that exact state that you were.
Within some accuracy. Well, the collapse has happened here. So when it goes from a superposition state to one of the eigenstates, that's where the collapse has happened. When I'm resetting, I'm sort of starting fresh. So yes, after the first, if you have created this state, it will have 50 probability to go to 0.
You are creating number of new experiments.
Yes, exactly.
Continue.
So these are technical details, depends on how the experiment is done. Sometimes it is the same system. You prepare it, you measure it, you reset, prepare, measure again. Sometimes you can have many copies, different physical systems, all of them prepared in the same state. Then you measure this one, you measure this one, you measure this one, but they're all starting at the same point. Okay, so those are technical details, depend on the exact physical system one is using. Okay. Yes, we can. That is how we are defining it here. But the ground state and the first excited state is really because of the particular example. In the case of light, for example, they are different polarization states. They don't have any different energy. It's the same energy. So they don't differ in energy. So the energy difference aspect is not important. That's just a consequence of the example I've chosen.
In that particular case, the polarization.
Exactly. So the 0 can be replaced by horizontal polarization, and 1 can be replaced by vertical polarization. The rest of the argument remains the same. So there, the measurement will be of the polarization. Okay. And then if you create some polarization which is in between the two, then that is basically what a superposition state is. Okay. In fact, that argument is going to come just now. So I want you to look at this picture carefully and realize that this measurement I'm talking about energy is sort of measuring the direction of this spin along this vertical direction. Let's call that the z-axis. Okay. So if the state is along the same axis, then that is the situation where you get the same result as 0 or 1. But if the state is now not along that axis, remember this particular point, so this is the z-axis, and now the x, this is pointing sort of along a 90-degree axis. That is what is called the superposition for this basis, okay? So it turns out that you can switch these around. I could have easily chosen this as my main axis and done a measurement along this axis, in which case this pink vector is no longer a superposition state for that choice of axis. Okay, so it's getting slightly complicated, but this is possible. So this is what I'm trying to say here, is that what is the superposition state and what is the measurement axis, sort of they together determine what is going on. So the thing you have to remember is that you can think of the measurement as choosing an axis and asking the question, is the vector pointing along the axis or anti-parallel to the axis? So we can now assign them, instead of 0 and 1, we call them +1 and -1, which means +1 means along the axis and -1 means anti-parallel to the axis. And the probability of whether you'll get +1 or -1 will depend on what axis you choose and what is the angle of the state with respect to the axis. So if you go back to the original choice of axis, which was Z, so these, this is anti-parallel, this is parallel, and this one is pointing 90 degrees. So that's why this one will give you random probability for when you measure along this axis. But I could flip the situation and I say that I'm going to choose this axis, the x-axis, as my measurement axis. Then this state could be either pointing along it or anti-aligned to it. But now 0 and 1 in the original basis become superposition states because they are 90 degrees with respect to each other. Okay. So this is an important thing to keep in mind to understand what happens in the Bell's inequality experiment. Okay. So far we're okay with this? All right. So let's move on. So now we bring the picture of quantum entanglement and we move on to what actually happened. Okay. I have now extended the system to two different qubits. Okay. So I have one qubit, which I've called alpha 0 plus beta 1, and alpha 2 0 and beta 2 1. Okay. Now, it is possible that when you consider a 2-qubit system, remember the 1-qubit system had two possible values, zeros and 1. Just like we can consider a 2-bit system, in a 2-qubit system, you can consider that there are now actually 4 possibilities: 0 0, 0 1, 1 0, and 1 1. So now there is an alternate way of thinking about the system, that, okay, this is a system with 4 states instead of 2 states for a qubit. And then the most general state is a superposition or a combination of all of these 4 different possibilities. And that is, I can now write, I've used a different symbol here called gamma 0 0 into 0 0, gamma 0 1 into 0 1, gamma 1 0 into 1 0, and gamma 1 1 into 1. So this is the most general description of any 2-qubit state you could have. Okay. But how does it connect to this alphas and betas which I've written down for the 2 qubits here? So one way, if we have 2 qubits, it is also possible to write down by combining these two things together. So remember, you see now here that the 0 0 has alpha 1 and alpha 2. The 0 1 has alpha 1 and beta 2, and so on and so forth. Okay. So this is also a way of writing down a 2-qubit state if we know that the first qubit is this one and the second qubit is given by this one.
Question here is strange.
Yeah.
Why we always consider it as a linear combination?
You mean why linear combinations are allowed and why not other combinations?
Yes.
That's because the equation is linear. So what does it, how do we know this? So when we take an equation and we find a solution, what that means is that if I plug in that solution, the left-hand side will be equal to the right-hand side. Now I have a second solution. There also the left-hand side is equal to right-hand side. Now I'm saying, let me add these two solutions and plug it into the equation. If you do multiply or you do any other thing, left-hand side will no longer be equal to right-hand side, and hence it is not a valid solution. Okay, so it's not some random thing we are choosing. What the mathematics tells you is that only if you combine the two individual solutions in a linear way, will it remain a solution of the equation? You can, of course, combine it and do anything, but it will no longer be a solution of the wave equation, which means it is not a valid solution describing the physics of the system. Okay, that's all there is to it. There could be some other complicated equation where some other combination might give rise to things, but most for quantum mechanics and also for waves propagating, it's the linear combination. Yes. It's not a preference, right? We have an equation. We have an equation which describes, or will Schrodinger put forward that this describes the reality of subatomic systems. That equation turns out to be linear, and hence the mathematics says that only linear combinations of solutions will remain solutions. There is no preference. You can try a nonlinear combination, it just won't satisfy the equation. And if it doesn't satisfy the equation, then it is not something you will see happen in real life, right? That's all. There is no preference here or anything. It's not that somebody decided to come up with a linear equation for quantum mechanics. It just, that's what it turned out to be.
Now you're taking two qubits. Assuming that there were 2 bits, we will again get 0, 0, 0, 1, 1, 0, 1.
Yes.
So the gamma 0 subscript 0, 0, 1, alpha. What does that now represent?
So if it was a classical 2-bit system, then this equation has no meaning, because this is representing a superposition of 4 quantum states corresponding to 0, 0, 0, 1, 1, 0. In the classical case, it will be one of these 4 possibilities at any point of time, right? This is the main difference. If you have a classical 2-bit system, I can prepare either 0, 0, 0, 1, 1, 0, or 1, 1. But in a quantum case, I can prepare a superposition state as well.
So I'm having a question of
all these 4. Just like in the case of a bit, a qubit, I had the superposition of 0 and 1, which were the 2 possible solutions. Now I have 4 possible solutions to the equation. So any linear combination of those 4 combinations of those 4 solutions is also a solution. Okay. So now the point I was trying to make is that how do we connect these 2 pictures? If you look very carefully, and I want to create in this general scenario a state like this, which is gamma 0, 0 into 0, 0 plus gamma 1, 1 into 1, 1. All this means is that I have set gamma 0, 1 and gamma 1, 0 as 0. Okay, perfectly valid thing to do. But if you now compare this to this equation here and ask the question, what value of alpha 1, alpha 2, beta 1, beta 2 can give me a situation like this? And you will see that it's actually not possible to do. Why is that? I want to create gamma 0, 1 equal to 0, right? So that is basically this term. So I can either set alpha 1 equal to 0, but if I set alpha 1 to 0, this will also become 0. If I set beta 2 equal to 0, then this will become 0. If I set beta 1 equal to 0, this will become 0. And if I set alpha 2 equal to 0, this will become 0. So you see that these 2 pictures are actually not compatible, even though it looks like they're talking about the same thing. And this is one very, very important concept of entangled states. By the way, this here is an example of an entangled state, is that there is no description of an entangled state in terms of the individual identities of the 2 partners which are making up the entangled state. What does that mean? Is that there is no value of alpha 1 and beta 1 and alpha 2 and beta 2 I can write down, which will give me this particular state. Okay, and this is really the strange part, is that they are always in a state where you can only describe them together. We cannot say that in this entangled state, qubit 1 is like this and qubit 2 is like this. We can only say that together they are like this. So this is the key point of what an entangled state is. Okay, so I hope this, I'm repeating it over and over again, but this point is very important. Yeah, all 4. So sum squares of all 4 of them should be equal to 1. So the normal, this is called the normalization condition. basically the total probability, because we are saying the system can only be in one of these 4 states. So the probability of finding them in all of those should add up to 1. And this fact that they don't have individual identities in this entangled state also means that at some point, if the qubits were not entangled, in order to create entanglement, you have to make them interact in some form. And then they can become entangled. If they are not interacting with each other, then you cannot do anything, because that only means that I can change alpha and beta independently, and I can change, alpha 1, beta 1, and I can change alpha 2, beta 1 independently. But we just saw that no such value is going to allow you to create this entangled state. Okay. So some special type of entangled states, which are also called Bell states, are of this type. These are again sort of the equal things with 0, 0 and 1, 1 having either a plus sign or a minus sign. You can also have an entangled state between 0, 1 and 1, 0 as well. Okay. Now we move on to the measurement of this entangled state. Is that if we now try to find out the properties of an individual qubit in an entangled pair, and here is a subtle point. I just told you that they don't have any individual properties. Okay. What that means is that I cannot write down the wave function of the individual qubits in this form. It does not preclude me from making a measurement to find out what state it ends up in. Okay, so these two are slightly different things. And now what I do is that if I have states like this, let's take, for example, this first state here. If I measure the state of only the first qubit out of this pair, and again, I'm going to choose the standard axis, the z-axis. So I'm going to be looking for answers which are 0 or 1 or plus 1 or minus 1, depending on what you want to use. The measurement on the first qubit will yield a random result of either plus 1 or minus 1. And that's because, both combinations are present. But the moment the result of the first qubit is fixed, the second qubit's identity is also fixed. The reason is because these zeros and ones come in pairs the way they are here. If the result of the first measurement was 0, then the only state with 0 is the 0, 0 state, right? So if the first qubit is 0, then the second qubit must be 0. If the first qubit is 1, the second qubit must be 1. So you can infer it, or you can go and measure and verify that it is indeed 1. Okay. So this is again just an extension of the superposition idea and the randomness of results. So remember, the result of the first measurement is going to be random. You can choose either the first qubit or the second qubit to measure first, and it will give you 0 or 1 or plus 1, minus 1 randomly. But the moment it is 1, the other one is frozen because of the nature of the 2-qubit wave function here. And so you might say, what's the big deal here? And this is where you have to understand the importance and the objections people had, or the concern people had at that time. If these two states belong to two electrons which were right next to each other inside an atom, or two atoms close to each other, we might not even think too much about it. Okay, that's what quantum mechanics is. So what's the big deal? The big deal happens if you are able to separate these entangled pairs after they have become entangled and take them far away from each other. Okay, that's where the problem lies, is that, or at least the way the problem was phrased, is that if now I measure one of the qubits or one of the electrons, which is in one location now, but remember they were initially entangled, quantum mechanics still says that the state of the other qubit is immediately determined the moment you measure the first one. So now the problem is phrased is that how does the second or the first qubit know what happened to the other qubit? Forget that the result of the measurement was plus 1 or minus 1. The very fact that it was even measured, how does this know? Right? Because we have this notion that if there are two bodies whose properties are correlated, then something must be going on between the two of them. Right? There has to some way this information, because the measurement is an act. How does the second qubit even know that the first one was measured? This is where the whole mystery of what quantum entanglement means started to bother people, right? And particularly, the problem becomes more crazy or becomes more difficult to believe when you say that if these two qubits were far, far away. Again, these were all thought experiments. Nobody could imagine creating an experiment where something was entangled and was taken to a different galaxy. We did not even have rockets at that time. But you could think that if something was so far away, quantum mechanics is still saying, because the space aspect is not even coming into the picture when we are talking about this. So how is this possible? So Einstein and others concluded that this must be wrong because it doesn't seem to agree with our common sense notions of what this is going on. Okay. But there are two important assumptions here about, and this is why, in the title of my talk, which I said, shed light on reality, there is this idea of what is realism and what is local. Okay. Local here means that if there is an object, it can only be influenced by its surroundings. More specifically, only things which are at a distance over a period of time where light can travel, only that distance it can influence. If something is too far away, any signal from that object takes a finite amount of time because it has to travel at the most at the speed of light. It cannot influence the property. So we start with that assumption, and it seems like a reasonable assumption to make. Okay. And the second thing is that any property of an object has to be associated with things which are on properties of that physical object only, not of something else further away. Sorry, the question here. The most general 2-qubit state has 4 different combinations. But an entangled state of 2 qubits has only 2 combinations. It's a subset of all the possible states. So maybe this is an important point to clarify. Not all 2-qubit states are entangled states. Particularly, if I have qubit in this state and qubit 2 in this state, the joint state of that is definitely not an entangled state. In fact, it's not entangled at all. And it's not entangled by the very fact that each qubit has individual identities. Okay. Is that clear? So it's a special class of states which is created. So these 2 points about fact that things can only be influenced at maximum at the speed of light. So something has to be close by, and properties of an object are only associated with things which are actually connected to that particular object. Sorry.
Doesn't make any relevance to measure both of them at the same time?
So you can, it makes absolutely no difference to the result. So what I mean by that is you could measure the first qubit and find it in 0, and you'll find that the second qubit is also measured to be in 0. You can measure the second qubit first and then the first qubit, or you can measure them at the same time. You will either both get 0 or you will both get 1 if this was the entangled state. And if this was the entangled state, you will see that they will always be opposite. If one is 0, the other one will be 1. Okay. So the entangled state determines what the correlation is, whether it's positively correlated or anti-correlated. Yes. Do the states fluctuate? Can you elaborate on what you mean by fluctuate? Yes.
So is it like, do they change frequency or do they change it according to pattern?
So okay. So that's actually the wrong way of thinking about superposition. So it's not even particular to an entangled state, right? When I talk about a superposition state between 0 and 1, I should not really think of this as something fluctuating between 0 and 1. Mathematically, it's a very precise state. It's 0 plus 1 over root 2. When I measure it, it will randomly give the result 0 or 1 with equal probabilities. If I repeat the whole experiment over and over again, that's how I'll be able to verify that it is 50% 0 and 50% 1. So you should not think about it. And this, in fact, is one of the central things which is confusing about quantum mechanics. And the accepted thing is that to think about what is happening in a superposition state is, in some sense, a moot question. It doesn't mean anything. You do the experiment, you do whatever you want to measure, and then the result will agree with the predictions of quantum mechanics. At least I believe, I belong to that school of thought, is that it's like the same thing when I showed you those funny shapes of electronic orbitals. You can keep wondering, where in that orbital the electron is. Maybe it's moving around very quickly, or it's like going around in some pattern very, very fast. Those questions, or the answers to those questions, have no consequence on any experiment you can do. What I can do is I can do an experiment to find the position of the electron after I have prepared it in a particular orbital. This is actually a very complicated experiment to do, but if one could do that, you will find it randomly in any of those positions. But if you redo it over and over again, you will see that that shape will come. And wherever the probability is 0, you will never find the electron in those locations. Similarly, if it's a superposition between two energy levels, then if I measure, I'll find that sometimes it's in the lower energy level, sometimes it is in the higher energy level. But those results are after the measurement. So to ask what is happening before the measurement is, in some sense, an irrelevant question, unless you, of course, know that this is the state. Then that's all you can say. So the wave function is basically supposed to give you the complete knowledge of what will be the result of any experiment that will follow. To really think about what is going on is actually sort of irrelevant, and there is no answer to that question.
Is it a way saying that if you ask me a question about singularity, what happens before the singularity?
I'm not sure if the two are of the same type of questions, but here answers to those questions have no implication on any experiments we can do. They only may help you sleep better at night. If you think you understand. So we belong to the school of thought where we sleep better when we don't ask those questions. Right. Yes, please. Yes. Okay, that's a complicated question. It's not exactly the same. So there is a difference between allowing for all possible paths versus in a measurement where it is found. What happens is that summing over all of those paths gives you a probability distribution. And what you will find out that if we talk about the standard case of, let's say, light traveling from one point to another in space, there is a probability that light will go straight. There is a different probability that the light will go like this. And there's a different probability the light will go to you and then come back. And what you will find is that as you make more crazier and crazier paths, those probabilities will cancel out. At least that's my understanding of this. But let's not go that this is sort of slightly outside the scope of what we're discussing. And I should move quickly so that we can finish on time. Yeah.
Is it possible to track states differently?
Is it possible to extract states in an, is it saying entangled state or? Yes, you can if those objects are separated. So we can measure one of the qubits and find out. So this is what I said a little while ago, that when in an entangled state, I cannot assign a wave function to one of the qubits. I can only assign it to the joint system. But when I make a measurement, I can make a measurement on one of them, and I can use quantum mechanical methods to calculate what will be the probability of the result on that measurement on one of the qubits. So that's what tells me that here I will get a random result for the first measurement, and the second measurement will be correlated. And it doesn't matter which order you do it, or if you do it simultaneously as well. So if you do it simultaneously, you'll randomly get 0, 0 or randomly 1, 1. And there are even types of measurements where you, instead of measuring the individual properties, you can measure the joint properties. So the measurement itself actually is along, now this axis is something you cannot draw on this, but it basically is saying, tell me whether it is 0, 0, 0, 1, 1, 0 or 1, 1. So it will give you one of these 4 results directly on the joint state. So such type of measurements are also possible. In fact, some subset of those are often called Bell type experiments. Okay. So let's get back on track. So again, all the strangeness really gets exaggerated when we start thinking about separating these objects and saying that how is it that the result of measurement on one seem to affect the other instantaneously. And this is what was bothered people. And we'll come back to this EPR paradox paper, where Einstein, Podolsky, and Rosen wrote this paper in 1935, saying that, you know, it cannot be a simpler title than this. And can quantum mechanical description of physical reality be considered complete? Right? And this is basically what they said. So EPR, in this, EPR is the, you know, the first letters of these 3 scientists. They describe the principle of locality as asserting that physical processes occurring at one place should have no immediate effect on the elements of reality at another location. This is what I said just a little while back. This is what they mean by the principle of locality. You cannot have instantaneous effects of objects which are far away or which are at any distance from you. So based on this, they concluded that quantum theory did not provide a complete description of reality, because entanglement seems to suggest that there is this instantaneous effect. You know, I keep using the word seems to suggest because that's very important, because actually it does not. And this is what Einstein also termed as spooky action at a distance, because how is this even possible? Okay. And they then said that this now must be happening because there is some set of hidden variables or hidden properties of these entangled objects, which we right now don't know what they are, but they predetermine the answers to the experiment. So what they mean by that is that they're saying there is some property of the object when these entangled particles are created, they pre-decide that, look, you come 0, I will also come out to be 0. Or you come out to be 1, I will also come out to be 1. And those properties travel with them, and then they are far away. Then this is already pre-decided, so it doesn't matter. You don't need any signaling. You measure the first one, you will get some answer, 0 or 1. And then since the other one is already pre-decided, this will give you the perfect correlation, right? And if you have seen many videos, people talk about pairs of gloves. If you put them in 2 boxes, if you find one of them to be the left pair, the other one has to be the right pair, because this is pre-decided. But this assumes that the result of the measurement, 0 or 1, was already present in the object itself before they got separated and sent their different ways. Quantum mechanics actually says that that is not true. And this is not just for entangled particles. This is actually just true even for a single superposition state. And this, in fact, even earlier, Einstein had said, you know, God does not play dice. This is referring to the fact that how is it that the result of a measurement on a superposition state is random? Where is this randomness coming from? So there also the idea is that there is some hidden property which is pre-deciding whether the answer is going to be 0 or 1. And every time we restart the experiment, it chooses a different value to start with. But it has nothing to do with your actual measurement. It is already recorded. You are just looking at it when you decide to look at it. Okay, so this important distinction, that's where the realism aspect comes in. They're saying that these properties are already there. Extreme example is like if there is a chair in the next room and it's blue in color, and suppose you have never seen that chair before. If you go and see it, it's blue. But if you have not seen it, does it not have that blue color already associated with it? Right? Okay, this is a simplified version of this argument, but that's what they meant. So they argued that these entangled particles already note down the results of the answers on themselves. So then there is no fast communication needed because they already know what answer they're going to reveal. Quantum mechanics says that is not the correct way to think about it. The property or the result of the measurement is not pre-decided. It happens at the time of the measurement. And then that is incompatible with this idea, or at least seems incompatible, that then somehow the other particle must know what has happened to the other guy. Okay.
One question about previous slide.
Yeah.
How does one explain entangled state in terms of energy eigenvalues?
So the energy eigenvalues are just the choice we have made for defining the state for each qubit. So the ground state energy is called 0. The first excited state is called 1. And similarly, you have the same for the second qubit. And the entangled state is just a combination saying that I'm now prepared a state where I have created a system where either both qubits are in 0 state, both in ground state, or both in excited state, or 0, 1 and 1, 0. So this was 1930s, and I think we can hopefully wrap up quickly now. There was absolutely no way to test any of these ideas. Okay. Till John Bell came along almost 30 years later, and he wrote this paper called On the Einstein-Podolsky-Rosen paradox. In fact, he read that paper and decided to come up with this argument. So I'll read out a few statements here. So Bell's theorem is a term encompassing a number of closely related results. There are actually many versions of it, which after he created the first one, which determined that quantum mechanics is incompatible with local hidden variable theories, given some basic assumptions of the nature of. So he has now qualified, and we have brought in a new qualifier, not just hidden variable theory, local hidden variable theory. Okay. Local here basically means that no faster than light communication is possible, even in a hidden variable theory. I will comment about that right at the end. And basically, his method allows you that if there was a local hidden variable theory, its experimental results will not be compatible with the predictions of quantum mechanics. So local here refers to the principal locality, that the idea that the particle can only be influenced by its immediate surroundings, and interactions mediated by physical fields can only occur at speeds no greater than the speed of light. So I already mentioned that. Hidden variables are hypothetical properties possessed by quantum particles, properties that are undetectable, but still affect the outcome of experiments. So this is like the pre-deciding what I'm going to give as a result of the answer. And what John Bell clearly said is that if a hidden variable theory is local, in this sense, it will not agree with quantum mechanics. And if it agrees with quantum mechanics, it will not be a local hidden variable theory. So his proposition was to distinguish between quantum mechanical predictions and local hidden variable theory. And he gave a formula for how to test that. Okay. And he considered two particles in a singlet state, which is a type of entangled state. But he now introduced this idea of measuring them along different axes. Okay, so this is why I had introduced this whole idea that you can define the states along one axis, but measure along a different axis as well. And that is very important for understanding Bell's theorem. Okay, so you can have different detector orientation. So basically allowed the possibility of making measurements along different axes, not just along the axis you decided to prepare the system in the original, which is the standard thing people do. Okay, and the result of each measurement is either +1, which means it's aligned along the measurement axis, or -1, which means it's anti-aligned along the measurement axis. And what he showed is that quantum mechanics predict that this probability for measuring them along different axes goes as this dot product of the two vectors. Don't worry about this aspect. But if it was a local hidden variable theory, which means the answers were pre-decided and decided to be correlated or anti-correlated, then they should satisfy an inequality like this. So here what it means is that probability of measuring the first one along A and the second one along B minus probability of measuring the first one along A and C should be less than equal to 1 plus probability of measuring the first one at B and C. So the B and C and A are just different detector orientation. Okay. So he basically showed that if you assume that the answers are pre-decided, then this kind of an equation must be satisfied just from pure logic. Okay, I'm not going to the details of working through this logic. There are actually very nice videos on YouTube. There's one particularly I recently saw by this guy called Arvin Ash. You can check it out. And he goes through the simple mathematics. Actually, it's very simple mathematics. I will not go into it here. And what he showed is that for some combination of A, B, and C, the results of quantum mechanics will not agree with this equation. So let me reiterate, this equation will be always has to be true if the properties of the measurements are pre-decided, which is what a local hidden variable theory will do. What he showed is that if one uses the quantum formula for some angle between these different detector orientations, quantum mechanics will not agree with this result. So what that meant is that you could now do an experiment and test this for different detector orientations and see that if the inequality is violated or not. So this is what is called, all the experiments are called violation of Bell's inequality. Okay. So violation of Bell's inequality means local hidden variable theory is not valid and quantum mechanics is valid. Okay. And later on, many different versions of this, these combinations of probabilities and what type of measurements were done, which were more compatible with what you could actually achieve in experiments. So those are just extensions of this. There are other kinds of inequalities called the CHSH inequality and some more as well. Okay. So as I mentioned, you can see this YouTube video by Arvind Ash, where he goes through these ideas of what would happen if the detector orientations were chosen and the results were already pre-decided. And you can see how this inequality actually comes about from those very simple arguments. So now what is the basic experiment that needs to be done? You need some way of creating entangled particles, and you need a way to send them away from each other. Remember that this is important that they are far from each other, or at least separated. Otherwise, all of this mystery is not really there anymore. So naturally, at that time, the only thing we could think about which could naturally travel far away is light. And we know light is also described quantum mechanically. So all these experiments used light. Today, we can repeat these experiments in other systems, but physically separating them is still almost impossible in any other system, whether it's an electronic circuit, like in quantum computers of IBM and Google, or it's some trapped ion system, because there the qubits are usually frozen in space. Taking them far away is not possible. But as I said, quantum mechanics actually doesn't say anything about the spatial separation. We have added that complexity to make the whole thing appear strange to us. So of course, if you want to do an experiment, you have to test it this way. These experiments have been repeated in other systems without the physical separation, and of course they agree. They all violate Bell's inequality. Okay? And once you have separated them, you need detectors on both sides which can make these measurements and along different axes. Okay, because Bell said that you have to make these measurements along different axes to be able to compute that formula which he wrote down and calculate its value and show that it violates the inequality. And you have to correlate those measurements. That's what the final thing is. Okay, so people use entangled photons. You use polarizers. So I'm sure many of you have seen polarizers. These two things which you rotate with respect to each other, it becomes dark, and the reason is that they allow light of only one polarization to go through. So if the first polarizer is allowing only horizontal polarization and the other one is rotated 90 degrees, then there will be no more horizontal polarization. The second polarizer is only allowing vertical polarization, so no light passes through. This is actually a way of choosing the measurement axis. Because remember, I told you that for light, the quantum states they chose are the polarization states. It's either horizontal polarized or vertically polarized, or a superposition of both of those. So by using polarizers and detectors which basically give you a click if a photon is heard, is the technique they used to do this experiment. And you then check for this Bell's inequality violation by changing the detector orientation and calculating that particular probability. So we'll now quickly go through the three main experiments. The first one was done by John Clauser in the 1970s, and he used entangled photons to show that the Bell's inequality was violated. To create these entangled photons, he used an atomic cascade in calcium atoms to generate what is called polarization entangled photons, is what I said. So this is an energy level diagram for a calcium atom. Don't worry about it if it looks complicated. The idea is that there are these different energy levels the electrons can be, just like we discussed earlier. And what they do is they actually shine light on this calcium atom, which excites the thing from this state here all the way to this top state over there. And then the physics of calcium atoms and the quantum mechanical equations tells you that that is going to decay with a small probability to this intermediate state. And then the only way it can come down is by emitting two different. So remember, every time electrons change energy, they emit light, right? So that's what the photons come from. So when the electron emits a photon when it goes from here to here, and then it emits a photon of a different wavelength when it goes from here to here. And the physics of these energy levels, the quantum mechanics of these energy levels, tells you that these two photons will be entangled. So these are two photons being emitted. They're like different colors, different wavelengths here means different colors. And the physics of this cascade guarantees that they will be created in an entangled state. So this is how the states are not entangled. The photon which is emitted when the electron decays from this level to this level, and then from this level to this level. These are two different transitions, and it always happens in a jump. So it doesn't jump directly from here to here. It has to jump through this cascade because of what is called the selection rule of this particular atom. So the photon which is emitted at 5513 angstroms, this one gamma 1, and the photon which is emitted at 4227 angstroms, which is gamma 2, these two photons are entangled.
That means the photons, that is the even state, not a stable state.
Yes, none of these states are stable. No state is infinitely stable. These are particularly short-lived states because you do want the photons to be created quickly, and I believe they decay within 5 nanoseconds of being excited or something like that.
Gamma 1 is slightly older than gamma 2.
Older.
Yeah.
Yes, there is a time ordering here, but because it happens over a fairly short range of things, that can be taken care of in the experiment. But the
whatever the time, one is slightly older than.
Yeah, so here's my ignorance about these optical processes. I don't remember exactly how one thinks about the time difference of emission between these, but they cannot be very large. It has to be almost close to each other because they have to happen in a cascade. And the physics guarantees that the polarizations have to be different, and they will either be they will be in this entangled kind of state.
So there is a lab is almost.
Yes. Yes. But if they do come out at slightly different times, you can control the measurement time so that they arrive at the same time. So that part actually doesn't affect the results of the measurement. But here I'm a little bit unsure about the technicality here. Okay. Now, even though he demonstrated this, there was one particular problem, or actually two particular problems, which one could invoke to say that, this is why this is work, but it's actually not saying anything. One is the fact of the locality. Now, what was the whole problem earlier? The problem was, we are saying, how does one entangled particle communicate and tell that I have come out to be zero, you better come out to be zero, right? That's the picture we are imagining. Now, in principle, if you say that if the result of the detector is, if one detector comes out to be +1, it could send a secret signal to the other detector and say, hey, I came out to be +1, you please cooperate with me and come out to be +1, because we want to fool the experimenter, right? So you also think about the kind of arguments one has to make to really make the results foolproof. So we are really trying to think of we don't really know how that happens. No one has proposed how this secret communication can happening between detector 1 and detector 2, but you say, well, it's in principle possible, we just don't know it, hidden variable, right? And the argument here is that the way the experiment was set up, there was enough time for the detector 1 to have sent a signal to the detector 2 because they were close enough. And if you assume that the secret communication happens at the speed of light, then they could have in principle communicated. So this is also true for the experiments I told you with where qubits are right next to each other. So this, we cannot break the locality loophole. And the second thing was something called fair sampling. It's more technical, but it's basically the fact that many of these experiments, you have to discard them because the detectors they were very inefficient. They don't detect every photon which comes through them. They only detect about 7%, I think, at that time. So there, the secret argument is that, you have only looked at a very small subset of photons. Maybe all the other photons did not obey this thing. So maybe something is wrong. So again, it's a circuitous argument, but it was important. But again, people were not really worrying about this too much. So again, 10 years passed, and Alain Aspect, the second Nobel laureate, he improved upon this experiment, and he introduced a few important things and closed this one important loophole. So one change he did was that instead of using some kind of an arc lamp to excite, he was actually able to use lasers. So by that time, lasers were becoming more common, and that actually allowed him to improve the efficiency with which these photons were actually being generated. And also because these were laser beams, he could better focus them and do the experiment with a much higher precision. But the most important thing was this locality loophole. And this he did by placing the detectors far enough, approximately 12 meters, which means the light took about 40 nanoseconds to go from one to the other. And he arranged the detection events in such a way that there was no way that the result of the first detector could be transmitted to the second detector before the second detector actually did the measurement. So for that, this laser, using the lasers was important, because then you could send the beam further away. Otherwise, those beams would diffuse very quickly. So that was an important experimental breakthrough. And also, he figured out a way to change the detector orientation, right? Again, you can say that, the first detector in the previous experiment, the angles were pre-decided. So you could say, the detector communicated and told the other detector, look, I am being measured along this axis, so you better behave accordingly. Since we both know quantum mechanics, you just do that. So here what they did is that even when the photons are actually being created, they don't know what the detector orientations are going to be. So he made a very important experimental breakthrough, actually using water and acousto modulation. They actually set up standing waves in water to create a diffraction grating, which could be turned on and turned off. And if the diffraction grating was present, it would send the light in a different direction, and it would go to a different detector which had a different orientation. And if you could turn it off, it would go straight and go to a different detector. So they had two choices of detectors with different orientations. And when that decision of whether it will go this way or that way, that was created after the entangled photons were already created. So then you can say that, well, the entanglement, the photons are already created. They couldn't have pre-decided their answers based on the detector orientations, which scientists had already said before. Okay. Yes. No, I think in this particular case, it was opposite. So one was horizontal, the other one would be vertical.
The property of the chemistry that when the electron from
Exactly. So that is just a detail of which system was used. Depending on other types of systems, you can create other types of entangled states. And that has no bearing on the result, because all you want is correlation. Whether they are correlated in the same directions or the opposite direction doesn't matter. So these days you can change these choices. At that time, this was frozen. Okay. So you again see the kind of innovations they had to do to sort out this very subtle thing. None of these things made any difference in the result. The result always agreed with quantum mechanics and said that the local hidden variable theory, but it ruled out any mysterious way the nature is working to, to deliberately spoil your experiment. Okay. So finally, Anton Zeilinger in the 90s, he made lots of, right now we are now entering the modern era of experiments. So he did many improvements in the experiments, which improved the overall quality. One of the things was that instead of using these calcium-based atom entanglement sources, there's now a new technique which uses nonlinear crystals, where you send light into a nonlinear crystal and two beams come out and they will be entangled at a particular angle. And this is actually the modern way of creating entangled photons even today. So that was pioneered at that time by Anton Zeilinger. It was a highly efficient source, get lots of light out of it. They did this thing where the detector orientation was completely randomized. So in the previous experiment, they had two different choices. Here you could choose anything, and they used the random number generator to decide what the orientation is going to be. There was no way then the photons at the time of creation could know what the detector orientation was. They even went to this crazy extent where they use, now you can always say, well, who is generating these random numbers, right? Maybe the computer program which was generating the random number had communicated secretly that, look, I am going to give 0, 1, 1, 0, 1, 0. So you decide according to that. So they used light from stars and quasars as the source of randomness, because those lights will have some fluctuation, and then based on those fluctuation, you can decide which detector orientation to choose. And the argument was that, look, this light was created billions of years ago. There was no way it could have any impact on what is happening right now. So they went to some crazy extremes to close all these different kind of loopholes. And finally, one very important loophole was also related to the efficiency of the detector, which I had mentioned. It's called the fair sampling thing. They finally were able to improve the efficiency close to about 90%, which means 9 out of 10 photons were detected, only a small number were discarded. Whereas earlier, only 1 out of 10 was detected. So by this, they could rule out any other kind of conspiracy where all the photons that are detected, they give you the answer you want and everything else gives you a different answer. But of course, we don't know what that is. Okay. So he also was able to do experiments involving more than 2 particles. So I only talked about entangled states with 2 particles, but you can have it with any number of particles you want. So for example, you can have a state 0, 0, 0 plus 1, 1, 1. Okay, and it's exactly the same. Now the correlation is even stronger. The moment the first one is measured to be 0, both the other 2 will be frozen to 0. If the first one is measured to be 1, both the other will be frozen to 1. And you can extend this to any number of qubits you want. So I think he did experiments using 3 and 4 states combined. But the most important experiment he did was the demonstration of something called quantum teleportation. And this is the last thing I will discuss before we stop. And this is the idea of transmitting a quantum state from one location to the another using entangled light. Okay, this is nothing like the Star Trek teleportation. You cannot transmit physical objects. The idea is very simple. The way to think about it is that, let's say you had a photon here and it was in a particular superposition state. And then you have a photon somewhere else, which is, let's say, just in its ground state. The teleportation would take this state and transfer it to that photon state, but it would actually be a teleportation because this original state gets changed. Okay, it's not a copy, it's a transmission in some sense. And this transmission happens without actually sending anything, but instead of doing measurements, careful operations using entangled states of light. Okay, so the details are very complicated, but the essence is this. You have a source of entangled photons. One goes to Alice, the other one goes to Bob. So now these 2 parties are sharing one copy of the entangled pair. There is an initial state. This is the state you are actually trying to transmit or teleport. You do a particular kind of interaction between this initial state and one of the entangled pairs. Actually, what you do is that you create an entanglement between these 2 and measure it in a particular way. And then you transmit the result of the measurement to Bob, who then performs, based on the result of this measurement, he performs a different operation, and that then transfers this initial state to the state here. Okay. So the sharing of this entangled photons is important, otherwise this will not work. But also you note that you have to send the result of the measurement as well to the other party. So even this is not instantaneous. Because if you don't send this information, Bob will not know exactly what to do. What is the reason? Because the result of this measurement here is going to be random again. It's going to give you some 4 different random answers. And Bob needs to know which random answer they got in order to recover the state correctly on the other side. Otherwise, you will only get the correct answer, maybe 1 out of, I think, every 4 counts as well. Okay, so that's what this is. But this is an important protocol, because the ability to transmit quantum states from one point to another is going to become extremely crucial as we build all these quantum technologies and if you're doing quantum communication. So this protocol is actually used in many applications today. So that's what the last slide is about. These days, entanglement is routinely used, and you can use other kinds of physical systems like superconducting qubits, which is my field of expertise. trapped ion qubits, photons, spin ensembles, and etc. Entanglement plays a key role in many quantum algorithms. The idea that you can create many qubits in a giant entangled state plays an important role in achieving these speedups, which we hear about in quantum algorithms. It also is extremely crucial for something called quantum error correction in quantum computing. Now, I'm sure many of you have heard about this idea of quantum computing, and you also know that these qubits are all unstable, right? We prepare them in some state, but they very soon all come back to the ground state or lose their phase information. So using such unstable qubits, you cannot hope to build a practical quantum computer. All the computers which are available today, the ones which are available freely on the internet and the things you read about, they all suffer from these errors. But people figured out that it's possible to use entanglement to store the information amongst multiple qubits which are entangled together. And if one of the qubits decays, it is still possible to recover the information by looking at the other qubits in a special way without actually knowing what the state is. Because remember, if you try to know what the state is, you will collapse it. What we are trying to build here is a memory where you have stored some wave function and you just want it to be stored for arbitrary long time. And instead of storing it in one qubit, you store it amongst multiple qubits which are in this entangled state. It turns out that you can actually protect them by constantly checking individual qubits for errors, and you can then correct them as well. And this is going to be a very, very crucial technology if you want to build practical quantum computers. Proof of principle experiments have showed that this idea works, but no one has truly implemented error correction till now. It's a big goal. And then finally, quantum key distribution, which actually uses photons to establish a secret key between multiple parties. And there are many protocols there, but one of them uses entangled photons. The idea is something like this. Alice and Bob each receive a photon from an entangled pair. They choose random bases for measurement and then discuss their detector orientations over a classical channel. And when they both use the same basis, they get correlated results, right? That's when the results are going to be correlated. And the trick here is that they basically want to establish a random sequence of numbers as their secret key. And what is the purpose of a secret key? That nobody else should know this secret key. So what this protocol does is that they actually use Bell's inequality violation test to know if somebody else has interfered. If some third party was actually observed the photon, because remember, any observation is going to affect the photon state, it will show up in the test of Bell's inequality violation. So if they see that the violation is there, then they know that everything is according to quantum mechanics and nobody could have interfered. But if somebody interfered in between, it will show up and then they will discard that code and establish a code again. So you see that how here entanglement actually plays a role in protecting information as well. And these are actually practical protocols which are even in operation today over small links. Okay, so that's basically it. I guess I had one last point to make. This is this idea of faster than light communication. Now, all of these experiments say that quantum mechanics is correct, which means that something spooky is still happening, right? Somehow the second, one way of thinking about it is that somehow the second part knows what has happened in the first part. But the answer here is that that part is actually, that way of thinking about it is not correct. I said this earlier, and the reason is that you have to not consider them as separate systems, but actually as the same system. The physical separation looks odd, but it actually does not change the wave function. The wave function is still a joint wave function. So the moment you measure anything about the wave function, it collapses everywhere at the same time. Now, if you start thinking about what is actually happening, is there some field there, then you will not be able to sleep. Nobody knows, okay? And this is the current state of understanding. And as I said, it doesn't seem to have any practical relevance on anything we can do today. Now, maybe tomorrow some experiments will show that there are cases where you can see this effect happening, and maybe we will have a different understanding which will complete quantum mechanics. But as of now, we cannot say anything is needed to fix this. Particularly, it's an interpretation problem. Now, this apparent instantaneous effect, can it actually be used in practice? And this is actually where people were wrong, especially even Einstein at that time, is that turns out that you really cannot use this to communicate at all. So let's look at this setup again. You have a source of entangled particles. One goes to this side, other goes to this side. Now, what is it you can do? You can only measure here and there, right? But if you measure something here, and if they measure something there independently, and if you repeat it over and over again, all you're going to get is a set of random zeros and ones, or plus ones and minus ones. That does not amount to any communication. In order for anything to happen in a correlated fashion, you need to send some information from A to B saying that, hey, I chose this axis and I got this result. Something of that sort. And that is done through a conventional communication channel, which can only transmit at the speed of light. So the apparent instantaneous spooky acceleration has no practical use at all. So it does not violate special relativity in that sense. So this is, I think, the part which they did not appreciate at that time. And now, you will see this argument being made anywhere. This apparent correlation between the entanglement cannot be used for any practical communication. You will need always a classical communication channel to do anything useful with it. So entanglement cannot be used to communicate faster than light. And you really have to consider entangled entities as a single system, even if they are spatially separated over, long distances as well. Okay. So I'll end the talk there, and let's appreciate all the work these three guys have done over the last 3 years. And thank you. Yes. Yeah, and then I can answer questions in person. Okay.
So it says that polarization of photons of different wavelengths is measured, and a limit placed on the granularity of space that is less than 10 raised to minus 48 meters is basically below the Planck density.
I see. Yeah, I'm not sure what aspect of granularity we are talking about. These experiments did not put any limits on the granularity of space. Not at all. Okay.
Okay.
All right. Thank you. And